Welcome to our exploration of climate change. In this video, we'll unravel the difference between climate and weather, dive into whether Earth is truly warming, and explore how typical were such changes in the past. We'll also take a closer look at the greenhouse effect, learn from the fates of Venus and Mars, and understand the crucial roles of carbon and water cycles. We'll discuss the human impact on our climate, look ahead to future projections, and examine the potential impacts on our world. Finally, we'll touch on the relationship between energy and climate, and suggest actions for the future. Feel free to watch the entire video to get a complete picture, or skip ahead to the sections that interest you most. The timestamps below will guide you through the different topics we'll cover. Before we dive in, it's important to distinguish between two key concepts: weather and climate. Weather is what we experience day to day, a sunny morning that turns into a rainy afternoon, or a sudden snowstorm. Climate, however, is the long-term pattern of these weather conditions over extended periods, typically decades or more. Think of it this way: weather is like a single scene in a movie, while climate is the entire film, showing the average of all those scenes combined. Climate encompasses several key elements, including average temperatures, precipitation patterns, humidity levels, and wind patterns. These factors combine to create the overall climate of a region, shaping its seasons, ecosystems, and even the way we live. It's important to remember that a few unusually hot or cold days don't change the overall trend. Just because we have a cold winter doesn't mean the planet isn't warming. Climate is about the bigger picture, the long-term trends that tell us how Earth's systems are changing over time. So, is Earth actually warming? To answer this, scientists have been meticulously measuring the planet's temperature. Here's a graph showing global average temperatures from 1880 to the present. The temperatures are shown as deviations from a baseline average, which in this case is the period between 1951 and 1980, a time often used as a reference. Overall, Earth was about 2.5 degrees Fahrenheit, or about 1.4 degrees Celsius, warmer in 2024 than in the late 19th century, 1850 to 1900, pre-industrial average. If we look closely, we can see that temperatures were relatively stable from the late 19th century until about the 1970s. But from the mid-20th century onwards, especially from the 1980s, there's a clear upward trend. This rise in temperature is what we refer to as global warming. In fact, the last decade was the warmest on record, with new temperature records being set almost every year. While global average temperatures provide a big picture view, it's important to note that not all regions warm at the same rate. For example, land areas, particularly in the northern hemisphere, have warmed almost twice as fast as the global average. This is because oceans can absorb and store more heat due to their larger capacity and the cooling effect of evaporation. In contrast, land heats up more quickly because it retains less moisture and has less capacity to store heat. The Arctic has warmed between 3 and 4 times faster than the global average. This accelerated warming is due to several factors, including the loss of sea ice, which normally reflects sunlight. As the ice melts, darker ocean water is exposed, absorbing more heat, a process known as the albedo effect. Additionally, black carbon deposits from pollution can darken the ice, causing it to absorb even more heat. The result is a feedback loop that accelerates warming in these regions. We'll explore the implications of this uneven warming in more detail in later sections. Since the late 19th century, Earth's average temperature has risen by about 1.4 degrees Celsius. This might not seem like much, but in terms of climate, even a small rise can lead to profound changes in weather patterns, sea levels, and ecosystems. We'll see in future sections why this seemingly small increase is so significant. Until now, we focused on the rise in global temperatures over the last century and a half. But temperature is just one aspect of a changing climate. Let's explore additional indicators of climate change, often called fingerprints, which go beyond just thermometer readings. The oceans are another critical area where warming is evident. The upper layers of the ocean have absorbed significant amounts of heat, leading to an increase in what scientists call ocean heat content. This accumulation of heat, particularly over the past few decades, highlights the ocean's role as a major heat reservoir, influencing global climate patterns. Shifts in temperature aren't limited to the surface. The lower atmosphere, or troposphere, has also shown signs of warming. Data from satellites indicate that the troposphere has warmed at a rate similar to or even slightly greater than the Earth's surface. In contrast, the stratosphere, the layer above the troposphere, has been cooling, a pattern which is, as we will see, consistent with the effects of greenhouse gas-induced warming. The cryosphere, which includes all of Earth's frozen water, is particularly sensitive to climate change. Mountain glaciers around the world are shrinking dramatically. For instance, glaciers in the Alps have lost about 50% of their mass since the 1850s, and others in the Andes has nearly disappeared. Globally, mountain glaciers have been losing around 335 gigatons of ice per year from 1994 to 2017. Arctic sea ice is another area of concern. Over the last few decades, the extent of Arctic sea ice, particularly in late summer, has decreased significantly. Not only is the ice cover shrinking, but the ice itself is thinning. Arctic sea ice is being lost with a rate of 12% per decade. This loss of Arctic sea ice is a clear signal of climate change, with significant implications for global weather patterns and ecosystems. Antarctica's ice cover is experiencing significant changes, with notable ice loss around the margins. Ice shelves are thinning and breaking apart, which accelerates the flow of ice from the land into the ocean. This increased ice loss contributes to rising sea levels and underscores the broader impacts of climate change on the continent. Greenland's ice cover is experiencing dramatic changes, with the Greenland ice sheet losing mass at an accelerating pace, which is a major contributor to rising global sea levels. A particular concern is the meltwater that seeps beneath the ice, potentially acting as a lubricant that allows the ice sheets to slide more easily into the ocean. Sea levels have been steadily rising, with an increase of about 20 centimeters, 8 inches, since 1880. The rate of rise has accelerated in recent decades, with satellite data showing a rise of approximately 5 mm per year since 1993. This rise is primarily due to the melting of glaciers and ice sheets, as well as the thermal expansion of seawater as it warms. Climate change also manifests in shifting weather patterns. There is evidence of more frequent and intense heat waves, as well as changes in precipitation patterns. While some regions experience more rainfall, others are becoming drier. This uneven distribution of precipitation can lead to droughts in some areas and floods in others. Additionally, more rainfall is occurring in brief, intense events, increasing the risk of soil erosion and other impacts on agriculture and infrastructure. Hurricanes are also changing in response to a warming climate. There is growing evidence that hurricanes are becoming more intense, with higher wind speeds and more destructive storm surges. Warmer ocean temperatures fuel these storms, making them more powerful and capable of holding more moisture, which results in heavier rainfall and increased flooding. Another subtle but important indicator is the narrowing of the diurnal temperature range, the difference between daytime and nighttime temperatures. This is primarily due to nighttime temperatures rising faster than daytime temperatures, likely linked to increased cloud cover. Climate change is also affecting animal behavior and ecosystems across the globe. Species are altering their migration patterns, breeding seasons, and feeding habits in response to shifting temperatures. For instance, birds are migrating earlier in the year, and some species are expanding their range northward as temperatures rise. Similarly, plants are responding to earlier springs by blooming and leafing out sooner, disrupting established ecological relationships and affecting the timing of food availability for various species. These indicators, taken together, paint a compelling picture of a planet in the midst of significant and rapid climate change. They provide additional, independent evidence that the warming we are experiencing is not just a temporary fluctuation, but a long-term trend with widespread impacts. But, how typical is today's climate situation? To answer that, we need to look beyond the 150 years of thermometer-based records. Scientists use various techniques to push our understanding of Earth's climate back thousands, even millions of years, revealing patterns that help us assess how unusual the current warming trend might be. Without direct temperature records before the mid-19th century, scientists rely on proxies, physical indicators of past climates. Tree rings, coral reefs, cave formations, lake and marine sediments, ice cores and fossils are key tools used to reconstruct past temperatures. For instance, tree rings can tell us about the length of growing seasons, while coral reefs provide information on ocean temperatures. Lake sediments offer insights into past snowmelt and springtime temperatures, and by analyzing isotope ratios in ice cores from Greenland and Antarctica reveal temperature fluctuations going back nearly 1 million years. By combining these proxies, scientists have reconstructed temperature patterns over the past 2 millennia. While temperatures gradually declined over much of this period, the 20th century saw a sharp and unprecedented rise. This suggests that Earth's current climate is likely the warmest it has been in at least the last 2,000 years. Comparing these reconstructions to historical periods like the medieval warm period and the Little Ice Age, it's clear that the recent warming not only differs in magnitude but also in speed, setting it apart from past natural variability. Even the comparison with data of the last 10,000 years shows that our current temperature is reaching record levels and continues the step-up trend like being in a rail coaster. Ice cores reveal a repeating pattern of ice ages and warmer periods, known as interglacials, over the past million years. These cycles, driven by subtle changes in Earth's orbit and tilt, are known as Milankovitch cycles. These cycles include variations in Earth's eccentricity, axial tilt, and precession, occurring over periods of approximately 100,000, 41,000, and 26,000 years, respectively. Typically lasting around 100,000 years, they have been key drivers of Earth's natural climate shifts. As Earth emerged from the last ice age, global temperatures rose by 4 to 7 degrees Celsius over about 5,000 years. In the past century alone, temperatures have risen by about 1.4 degrees Celsius, around 20 times faster than the average rate of warming during that ancient transition. Models predict that Earth could warm by 2 to 6 degrees Celsius in the next century, a rate that would be 20 to 60 times faster than past warming events. This rapid change is highly unusual and does not align with natural cycles, raising questions about its cause. To put this in perspective, our genus, Homo, has existed on Earth for approximately 2.4 million years. Our species, Homo sapiens, has been around for about 200,000 years, while human civilization, as we know it, has only developed over the last 10,000 years. Yet, the rapid climate changes we are witnessing now are occurring within just a fraction of that time, challenging the stability that our ancestors have relied on for millennia. Looking even further back, geological evidence and fossil records show that Earth has experienced both extreme warmth, like during the age of the dinosaurs, and extreme cold, such as during the snowball Earth phases. However, the current rate of warming seems to be much faster than anything observed in these past natural events. Importantly, today's climate is not a final stage but part of a dramatic uptrend. If current trends continue, the future could show even more stark abnormalities compared to historical patterns. What we're witnessing now is just the beginning of a potentially much larger shift. So, is today's climate typical? While Earth has gone through many climate changes over its long history, the rapid warming we're experiencing now appears to be abnormal, especially in the context of the last few millennia. Some skeptics argue that the changes could be part of a natural cycle, but we'll address those points of skepticism later during this video. Understanding this is crucial as we explore what's driving these changes in the next section. Now that we've seen how unusual today's climate is, the next step is to understand why. Let's delve into the greenhouse effect and its role in driving these temperature changes. Let's dive into a fundamental concept that is crucial for understanding what establishes Earth's climate: energy balance. Think of it like this: imagine a house. For the house to maintain a steady temperature, the amount of heat it gains from the furnace must be balanced by the amount of heat it loses through the walls, windows, and roof. If the house is warmer than its surroundings, heat flows out, and the rate of this heat loss depends on how much warmer the house is compared to the outside. Now, imagine if you were to increase the insulation in the house, adding more layers to the walls or using better insulated windows. With the same amount of heat coming in from the furnace, the house would become warmer because the heat would have a harder time escaping. To restore balance, the temperature inside the house would need to rise until the heat escaping through the small areas that still allow it to pass equals the heat being added. Now, let's apply this concept to Earth. Earth receives energy from the sun primarily in the form of visible light and ultraviolet radiation, with most of this energy concentrated in the visible spectrum. On average, this energy amounts to about 240 watts per square meter, equivalent to having 2.5 100-watt light bulbs shining down on every square meter of Earth's surface. But Earth isn't just a passive receiver of energy, it also radiates energy back into space. This outgoing energy is in the form of infrared radiation, which is invisible to our eyes but can be felt as heat, much like the warmth you feel from hot coals. This infrared radiation is crucial to maintaining Earth's energy balance. Here's where things get interesting. According to the Stefan-Boltzmann law, the rate at which Earth radiates energy increases rapidly as its temperature rises. This law helps us estimate that, without considering the atmosphere, Earth's average temperature should be about -18 degrees Celsius, around 0 degrees Fahrenheit. That's cold enough to turn our planet into a giant snowball. But thankfully, Earth's atmosphere changes the picture. The atmosphere contains greenhouse gases like water vapor and carbon dioxide. These gases are like a blanket, they let sunlight in but trap some of the outgoing infrared radiation, keeping Earth warmer than it would be otherwise. This is known as the greenhouse effect and more specifically the natural greenhouse effect. Our atmosphere is composed mostly of nitrogen, about 78%, oxygen, around 21%, and argon, about 0.93%, none of which trap heat. However, it also contains small amounts of greenhouse gases, such as water vapor, which can vary from 0 to 4%, carbon dioxide, about 0.042% or 420 ppm, methane, around 1.8 ppm, and many others in much lower percentages. Despite their relatively low concentrations, these greenhouse gases are the main drivers of the greenhouse effect. Water vapor contributes roughly half to 3/4 of the effect, while carbon dioxide accounts for about 1/5 to 1/4. Together with methane, these gases play crucial roles in trapping heat, making Earth's average temperature around 15 degrees Celsius, a much more comfortable climate than the frigid -18 degrees it would be without them. To understand the greenhouse effect further, consider this: greenhouse gases not only trap heat but also re-radiate some of it back to Earth's surface. This process requires Earth's surface to be warmer than it would otherwise be, ensuring that energy eventually escapes into space, maintaining a balance. Just like a house needs to balance heat gain and loss to stay warm, Earth's climate relies on balancing the energy it receives from the sun with what it radiates back into space. Greenhouse gases in the atmosphere are adjusting temperatures on the surface and within the atmosphere like the insulation in the house of our initial example. The greenhouse effect also involves the cooler upper atmosphere, which cannot radiate as much energy as the warmer surface. This imbalance requires the Earth's surface to warm up to help some of the energy escape through the nearly opaque greenhouse gases. If the upper atmosphere were as warm as the surface, there would be no greenhouse effect. The Earth's energy budget is a complex system, but it can be understood in simpler terms by looking at how solar energy interacts with our planet. When sunlight reaches Earth, some of it is reflected back into space by clouds, atmospheric particles, and reflective surfaces like ice and snow. The rest is absorbed by the Earth's surface and atmosphere, warming the planet. This absorbed energy is then radiated back as infrared radiation. However, greenhouse gases like water vapor and carbon dioxide trap most of this heat, but not all, in the atmosphere, and re-radiates it both towards the surface and towards the space. Additionally, energy is transferred from the Earth's surface to the atmosphere through thermals, which are rising columns of warm air, and through evapotranspiration, where water evaporates from surfaces and transpires from plants, carrying heat energy into the atmosphere. This natural greenhouse effect, combined with these processes, keeps our planet about 33 degrees Celsius 60 degrees Fahrenheit warmer than it would be without an atmosphere, making it suitable for life. There are many ways to disrupt this balance, such as increasing greenhouse gas concentrations, changing the amount of incoming sunlight, or altering Earth's surface reflectivity, like reducing snow cover. These disruptions can significantly impact Earth's energy balance and, consequently, its climate. How do we know that greenhouse gases are driving Earth's warming? While we have advanced experimental data and incredibly sophisticated computer simulations that model our planet's climate with remarkable precision, we also turn to historical climate records. By studying past climates and greenhouse gas concentrations, we can identify patterns and correlations between these gases and Earth's climate changes over millennia. Water vapor is indeed the dominant greenhouse gas, but it acts mainly as a feedback mechanism. It responds quickly to changes, cycling in and out of the atmosphere within days. When the Earth warms due to increased CO₂, the atmosphere holds more water vapor, which then amplifies the greenhouse effect. Carbon dioxide further remains in the atmosphere for centuries, gradually building up and exerting a longer-lasting influence on climate. If CO₂ diminishes in the atmosphere, leads to opposite changes both in temperature and in vapor levels. This makes CO₂ crucial for understanding long-term climate change. Ice cores are invaluable for studying past climates. They contain tiny air bubbles that trap ancient atmospheric gases. By analyzing these bubbles, scientists can measure historical concentrations of greenhouse gases like carbon dioxide and methane. When we look at climate data over the past 500,000 years, a striking pattern emerges. The graph displays carbon dioxide levels and global temperatures, revealing a close correlation. During ice ages, carbon dioxide concentrations were low, and global temperatures were cooler. Conversely, in warmer interglacial periods, carbon dioxide levels were higher, aligning with warmer temperatures. This relationship shows that carbon dioxide has been a key driver of Earth's climate changes, with higher carbon dioxide levels closely tracking periods of warmth and lower levels associated with colder ice ages. The data clearly illustrates how carbon dioxide has significantly influenced Earth's climate throughout history. The same correlation between carbon dioxide levels and temperature is evident even when we look at data over the past 800,000 years. A similar positive correlation is also observed for methane, the second most potent greenhouse gas. The strong correlation between CO₂ levels and global temperatures over the past years reveals a compelling relationship, but it's not a simple cause and effect scenario. Instead, it's driven by a complex interplay of factors. Earth's climate cycles, influenced by subtle changes in the planet's orbit, such as its elliptical shape, axial tilt, and precession, initiate initial temperature changes. These shifts can trigger a cascade effect. As temperatures rise, CO₂ stored in oceans and soils is released into the atmosphere, amplifying the greenhouse effect, leading to further warming. This, in turn, causes even more CO₂ to be released from the oceans and soils. This is a cycle of positive feedback that drives a relatively rapid rise in both temperature and CO₂ levels until interglacial temperature maxima are reached. Conversely, as the orbital parameters shift, these conditions diminish, causing CO₂ and temperature to gradually decline step by step. This intricate feedback mechanism helps explain why CO₂ and temperature levels rise and fall together over geological timescales, demonstrating the significant role of greenhouse gases in shaping Earth's climate. Looking further back in Earth's history, we observe even more dramatic climate variations. During the age of the dinosaurs, approximately 60 to 200 million years ago, carbon dioxide levels exceeded 2,000 parts per million, about 8 times higher than pre-industrial levels. Global temperatures were significantly warmer, allowing warm climate ecosystems to thrive even in present-day polar regions. Over these vast time scales, geological processes like volcanic activity, plate tectonics, and rock weathering played a major role in shaping the climate. Notably, the elevated carbon dioxide levels during the dinosaur era were largely due to increased volcanic activity and the breakup of Pangaea. The sun has always played a crucial role in driving Earth's climate, influencing temperatures over various time scales. Solar variations, such as changes in solar output and Earth's orbital dynamics, have led to periodic climate fluctuations. For example, the 11-year solar cycle affects short-term climate variability, while longer-term cycles like the Milankovitch cycles alter Earth's orbit and axial tilt, contributing to glacial and interglacial periods. During the 11-year cycle, the sun's output can vary by about 0.1%, impacting regional climates, especially in polar and mid-latitudes. While the sun's energy output has gradually increased over billions of years, Earth's climate hasn't experienced a simple, continuous warming. Instead, complex feedback mechanisms, such as the carbon cycle, volcanic activity, and the evolution of life, have regulated the climate, leading to both warming and cooling periods, rather than a straightforward warming trend driven solely by solar brightening. As an example of short-term effects, the Little Ice Age between approximately 1300 and 1850 CE experienced global temperature drops of about 1 to 2 degrees Celsius, resulting in harsher winters and shorter growing seasons. Reduced solar activity during the Maunder Minimum, 1645 to 1715, contributed to this cooling, but it was not the sole cause. Increased volcanic eruptions and changes in oceanic circulation also played significant roles, underscoring the complex interplay of factors that influence Earth's climate. Is the greenhouse effect a phenomenon that occurs only on Earth, or is it a natural principle in the universe? The comparison between Venus, Earth, and Mars offers a fascinating natural experiment that underscores the universality of the greenhouse effect. Venus, Earth's closest twin planet in size and composition, vividly illustrates the catastrophic effects of an unchecked greenhouse effect. Based on their distances from the Sun, without greenhouse effects, Venus should have a surface temperature of about 55 degrees Celsius, Earth around -18 degrees Celsius, and Mars approximately -50 degrees Celsius. However, the actual temperatures are vastly different. Venus, with its thick atmosphere of 96% carbon dioxide, has a scorching surface temperature of about 460 degrees Celsius, while Earth, benefiting from a moderate greenhouse effect, averages around 15 degrees Celsius. Mars, with its thin atmosphere, remains frigid at around -60 degrees Celsius. These differences highlight the critical role that atmospheric composition plays in determining a planet's climate. For Venus, the slightly higher initial temperature, due to its closer proximity to the Sun, triggered a runaway greenhouse effect. As the planet warmed, water vapor in the atmosphere increased, further intensifying the greenhouse effect and leading to the complete loss of water through photodissociation, where solar radiation split water molecules, releasing hydrogen into space. Meanwhile, volcanic activity continuously released massive amounts of carbon dioxide into the atmosphere, driving temperatures to their current extreme levels. In contrast, Mars' thin atmosphere exerts almost no greenhouse effect, leaving it cold and inhospitable. Earth occupies a middle ground, where its greenhouse effect has maintained a stable, life-supporting climate. This comparison illustrates that the greenhouse effect is a universal principle, with the amount of greenhouse gases, particularly carbon dioxide, crucially shaping the climate of each planet. It is crucial to investigate what happens to the water vapor and carbon dioxide naturally present in Earth's atmosphere. How do these substances adjust themselves within our planetary system to maintain the climate we experience today? While energy flows through Earth, entering as sunlight and leaving as infrared radiation, the substances within our atmosphere, like water vapor and carbon dioxide, cycle through the planet's system in intricate and vital ways. These cycles are essential to understanding how our climate remains stable. While there are many other material cycles, such as those of nitrogen, phosphorus, and sulfur, that also impact the climate, water vapor and carbon dioxide are particularly important because they are potent greenhouse gases. In this discussion, we'll focus on how these two substances naturally adjust within Earth's system, shaping the climate we experience today. Take water vapor, for example. Driven by solar energy, surface water evaporates and rises into the atmosphere, carrying with it latent heat. There, it forms clouds and eventually returns as precipitation, completing the water cycle. Despite its relatively short stay in the atmosphere, typically just about a week, water vapor adjusts quickly to temperature changes, making it a key player in regulating Earth's climate. Although it constitutes only a tiny fraction of the total water on Earth, which includes oceans, rivers, lakes, the cryosphere, and groundwater, its rapid cycling and strong dependence on temperature allow it to respond swiftly to changing conditions, significantly influencing the greenhouse effect. Understanding the carbon cycle is essential for grasping climate dynamics, especially the duration that carbon dioxide remains in the atmosphere. Unlike water vapor, which stays in the atmosphere for only about a week, CO₂ can linger for decades to centuries. This prolonged presence of CO₂ in the atmosphere is crucial for understanding its impact on climate change. The diagram illustrates the various reservoirs of carbon with white digits, such as the atmosphere, oceans, and living organisms, and shows the flows of carbon between these reservoirs with yellow digits. Red digits represent anthropogenic contribution and will be examined in a while. The contents are measured in gigatons, billions of tons, and the flows in gigatons per year. Let's start with the shorter-term carbon cycle, which involves rapid exchanges between the atmosphere, oceans, and living organisms. For instance, carbon dioxide dissolves in surface ocean waters, and this exchange is nearly balanced by CO₂ released back into the atmosphere. Plants also play a significant role by absorbing CO₂ during photosynthesis to create carbohydrates, removing about 120 gigatons of carbon from the atmosphere each year. Respiration and decay then return a large portion of this carbon to the atmosphere. In this rapid cycle, a typical carbon dioxide molecule stays in the atmosphere for about 5 years before being cycled back out, though some carbon ends up stored in soils and oceans. This shorter-term cycle is naturally balanced, with the amount of carbon dioxide leaving the atmosphere roughly equal to the amount entering it. These natural processes maintain equilibrium, excluding human contributions for now. In the long-term carbon cycle, carbon dioxide can remain in the atmosphere for much longer than the 5-year average of the short-term cycle. This is primarily due to two key processes, the biological pump and deep ocean circulation. The biological pump involves marine organisms that, upon dying, sink to the deep ocean, carrying carbon with them and effectively removing it from the short-term carbon cycle. Deep ocean circulation, driven by temperature and salinity differences, transports this carbon-rich water across the globe and stores approximately 37,000 gigatons of carbon in the deep ocean. While some of this carbon returns to the surface through processes like upwelling and diffusion, the net removal rate is about 2 gigatons per year. This slow exchange between the deep ocean and the surface means that CO₂ can persist in the atmosphere for hundreds to thousands of years, with some molecules potentially lasting up to 30,000 years. This extended presence means that any additional carbon we release can significantly impact the climate, influencing the greenhouse effect and global temperatures over extended periods. In addition to the above cycles, there are even longer-term geological processes that operate over millions to hundreds of millions of years. One key process is the formation of sedimentary rocks. Carbon that sinks into the deep ocean eventually becomes part of these rocks, which are later brought to the surface through tectonic activity. At the surface, these rocks weather and release their stored carbon back into the atmosphere, or the carbon is released through volcanic eruptions. Volcanism is another significant process, as volcanoes release carbon dioxide that was previously stored in the Earth's crust, contributing to the carbon cycle on geological timescales. Additionally, carbon that is buried before decomposing can transform into fossil fuels such as coal, oil, and natural gas. It is estimated that there is around 10,000 gigatons of carbon in fossil pool. These fossil fuels store ancient solar energy captured by photosynthesis. While fossil fuels have little impact on the natural carbon cycle, they become highly significant due to human extraction and use. Let's take a closer look at the human factor in shaping climate change. Is there solid evidence that human activities are driving the recent rise in global temperatures? And how does this influence compare with natural causes like the sun and volcanoes? The natural carbon cycle efficiently circulates carbon between the atmosphere, oceans, and living organisms, with carbon staying in this system for hundreds to thousands of years. However, human activities have significantly disrupted this balance. The burning of fossil fuels adds about 7 gigatons of CO2 to the atmosphere annually, while deforestation contributes another 2 gigatons. That is a total effect of 9 gigaton per year. Although these emissions seem small compared to natural carbon flows, they are crucial because the extra carbon accumulates over time, remaining in the atmosphere and enhancing the greenhouse effect. Before the Industrial Revolution, the atmosphere contained about 560 gigatons of carbon. Today, that number has risen to around 800 gigatons, a substantial increase driven by human activity. Importantly, while natural processes absorb some of this carbon, the net effect is that about 4 gigatons of CO2 are added to the atmosphere every year. Atmospheric CO2 levels have been steadily rising since the onset of the Industrial Revolution, increasing from approximately 280 parts per million in 1750 to around 420 parts per million today, a staggering 50% increase. This significant rise is primarily due to human activities such as burning fossil fuels and deforestation. Thanks to precise measurements in the last decades, we can observe not only the overall increase in CO2 but also the subtle seasonal fluctuations. These small wiggles in the graph represent the natural cycle of photosynthesis. During the spring and summer in the northern hemisphere, which has the most land, plants absorb CO2 from the atmosphere, causing a slight drop in levels. As winter approaches and photosynthesis slows, CO2 levels rise again. This seasonal pattern, superimposed on the long-term upward trend, illustrates the delicate balance of our planet's carbon cycle. The ongoing increase in CO2 is a clear and measurable indicator of the enhanced greenhouse effect, contributing to global warming and ongoing climate change. How do we know that the rise in CO2 is from human activities, especially fossil fuels? First, we track fossil fuel usage precisely, and this data aligns closely with the CO2 increase. Second, the carbon isotopes in the atmosphere have changed. Fossil fuels are low in carbon-13 and carbon-14, and as we burn them, the atmospheric ratios of these isotopes shift, revealing a clear fossil fuel signature. Lastly, burning fossil fuels consumes oxygen, causing a measurable, though subtle, decrease in atmospheric oxygen. Together, these clues strongly point to fossil fuels as the main source of rising CO2 levels. The rapid rise in CO2 levels during the industrial era is clear, but just how unusual is this increase in Earth's history? Are the current CO2 levels part of a natural cycle, or have we entered unprecedented territory? If we look back over the last 1,000 years, we see that CO2 levels remained relatively stable at around 280 parts per million until the onset of the industrial era. Around 1750, this stability ended as CO2 levels began to rise sharply, mirroring the significant uptick in global temperatures. This steep rise, especially in the last century, is unprecedented on this millennial timescale, closely correlating with the dramatic temperature increase we've experienced. When we extend our view further back, over the last 800,000 years, the pattern becomes even more striking. CO2 levels have naturally fluctuated between about 180 and 280 parts per million, closely tied to cycles of ice ages and warmer interglacial periods. However, the current CO2 level of around 420 parts per million, and rising, is far beyond anything observed in these natural cycles. In fact, today's levels are likely the highest seen in at least 1 million years, and perhaps even 20 million years. This extraordinary spike marks a significant and unprecedented human impact on the Earth's atmosphere, far outside the range of natural variability. Now, carbon dioxide isn't the only human activity that impacts Earth's climate. There are several other factors, each influencing the planet's energy balance, and thereby altering the climate. Methane. Methane is a potent greenhouse gas, about 26 times more effective than carbon dioxide at trapping heat. However, it's less abundant and remains in the atmosphere for only about 9 years. Sources include leaks from natural gas systems, agriculture, especially from rice paddies and livestock, and even decaying vegetation in reservoirs from hydroelectric dams. Though methane's impact is significant, contributing to about a third of global warming compared to carbon dioxide, it's complex and not fully understood. Aerosols. Human activities also emit aerosols, tiny particles suspended in the atmosphere. These include soot from burning coal and sulfate aerosols from industrial activities. Unlike greenhouse gases, aerosols tend to cool the climate by reflecting sunlight back into space. They also promote cloud formation, which further increases the reflection of sunlight. However, this cooling effect is mostly localized and insufficient to counterbalance the global warming driven by greenhouse gases. Other greenhouse gases. Other significant gases include nitrogen oxides, halocarbons, used in refrigerants, and ozone. Ozone's effect is dual. In the lower atmosphere, it warms the climate, while in the upper atmosphere, it cools it. Overall, these gases contribute to climate change in varying degrees. Land use changes. Human activities like deforestation and urbanization alter the planet's reflectivity. Deforestation can slightly increase albedo and cool the climate, while urbanization usually lowers albedo, causing warming. Overall, these changes contribute more to warming than cooling, especially when considering greenhouse gas emissions. Natural influences. Lastly, natural factors such as changes in solar intensity do influence Earth's energy balance, but their impact on recent climate change is relatively minor compared to human activities. With human factors playing a dominant role, these combined influences have led to a net warming of the planet. This context helps us understand the complex interplay between various climate factors and highlights the significant impact of human activities. So, could the sun be responsible for the rise in global temperatures, as some skeptics suggest? While it is true that the sun's energy output does fluctuate, evidence indicates that current global warming cannot be attributed to changes in solar energy alone. If solar activity were driving global warming, we would expect to see uniform warming across all layers of the atmosphere. However, what we actually observe is a distinct cooling in the upper atmosphere, stratosphere, alongside warming at the Earth's surface and in the lower atmosphere. This pattern is a key indicator of the greenhouse effect, as greenhouse gases trap heat in the lower atmosphere while allowing the upper atmosphere to cool. The phenomenon of stratospheric cooling is one of the most compelling pieces of evidence supporting the greenhouse effect. This vertical temperature pattern is inconsistent with solar-driven warming but aligns with expectations from greenhouse gas-induced warming. Furthermore, climate models that account only for variations in solar irradiance fail to replicate the observed temperature trends over the past century. These models accurately reproduce the warming observed in recent decades only when they incorporate the rise in greenhouse gases. The graph demonstrates this discrepancy. Despite a decline in solar activity since the 1960s, global temperatures have continued to rise, reinforcing that the sun alone cannot explain the current warming trend. This evidence underscores the dominant role of greenhouse gases in driving recent climate change. Some might wonder if volcanic activity, which does release CO₂, could be driving the long-term warming trend. While it's true that volcanoes emit CO₂, the amount they contribute is minuscule compared to the emissions from human activities. On average, volcanic CO₂ emissions are estimated to be less than 1% of those from burning fossil fuels. Additionally, volcanic eruptions tend to have a short-term cooling effect due to the large amounts of ash and sulfur dioxide they release, which reflect sunlight away from the Earth. While volcanism did play a significant role in shaping Earth's climate in the distant past, such as during periods of intense volcanic activity that contributed to mass extinctions and significant climate shifts, the current warming trend cannot be attributed to volcanic activity. Instead, it is overwhelmingly driven by human-induced greenhouse gas emissions. Solar activity and volcanism can explain the temperature variations before this century, but fail in the last decades due to the dominant human factor. Could human activities be driving the unprecedented rise in global temperatures? To find out, scientists use advanced computer models. These models simulate the Earth's climate system, incorporating physics, chemistry, and biology to predict climate behavior. By running these models with historical data, scientists can test if they accurately reproduce past climate conditions. Models that include only natural factors, like volcanic activity and solar variations, explain much of the climate variability up to the early 20th century. However, they fall short when it comes to the rapid warming observed since the mid-20th century. When human influences, such as greenhouse gas emissions and industrial aerosols, are included, the models accurately replicate the observed temperature trends. This clear match between modeled and real-world temperatures strongly indicates that recent warming is largely due to human activities. But why are we so concerned about climate change? Can just a few degrees of warming really have a big impact, or is it something we can afford to overlook? The truth is, even a small increase in global temperatures can lead to significant changes in our environment. The most obvious impact of climate change is the rise in global average temperatures, and how much they will rise in the future depends largely on our actions, like how much greenhouse gases we emit and how we use our land. In 2015, more than 190 countries, almost every country in the world, agreed to work together to tackle climate change. This agreement is called the Paris Agreement. The goal is to limit global warming to well below 2 degrees Celsius above pre-industrial levels, and ideally to keep it under 1.5 degrees Celsius. However, experts are concerned that the current efforts might not be enough. With the actions that countries have promised so far, global temperatures are still expected to rise by 2.5 to 2.9 degrees Celsius by the end of this century. Since 2010, we've made some progress. Back then, temperatures were expected to rise by up to 4.8 degrees Celsius by 2100. Now, with current efforts, the expected rise is between 2.5 degrees Celsius and 2.9 degrees Celsius. In the best-case scenario, if every country fully keeps its long-term promises, we might see an increase of around 1.7 degrees Celsius to 2.1 degrees Celsius. However, to truly limit global warming to 1.5 degrees Celsius, we need to act quickly, with emissions peaking by 2025. But keep in mind that even a small change in global temperature can lead to much larger shifts on land, with temperatures rising nearly twice as much, and even more so in the Arctic. These seemingly small increases have significant effects across the planet. Let's examine the most profound implications if the global warming intensifies. Weather patterns. As temperatures rise, we can expect more frequent and severe heat waves, which are already causing significant health problems and deaths. Heavy rainfall events are becoming more common, increasing the risk of floods, while other regions face prolonged droughts, leading to water shortages, crop failures, and the spread of desertification. By the end of the century, the extent of drylands could expand to cover 50 to 56% of the Earth's continents, particularly affecting regions like Southwest North America, the northern fringe of Africa, Southern Europe, Southern Africa, and Australia. Additionally, tropical storms and hurricanes are projected to become more intense due to warmer ocean temperatures, leading to stronger winds, heavier rainfall, and more severe storm surges. Compounding these issues, climate change is also expected to reduce the replenishment of groundwater resources, further straining water supplies in vulnerable areas. Sea level rise. As global temperatures increase, ocean waters expand and land-based ice melts, causing sea levels to rise. Over the past century, the global sea level has risen by about 16 to 21 centimeters, 6.3 to 8.3 inches. This rise is accelerating, with current rates around 3.3 millimeters per year. Projections for the 21st century vary depending on greenhouse gas emissions, with estimates ranging from a rise of about 30 to 120 centimeters, 1 to 4 feet, by 2100. This increase poses a severe threat to low-lying regions, such as Florida, Bangladesh, and small island nations, potentially displacing millions of people and leading to the loss of significant land areas. Additionally, rising sea levels increase the risk of coastal flooding, especially during storms and high tides. Saltwater intrusion is another consequence, contaminating freshwater aquifers and disrupting marine estuaries, which are crucial for the biodiversity and health of marine life. Ocean changes. The increasing concentration of carbon dioxide in the atmosphere is causing more CO₂ to be absorbed by the oceans, resulting in a decrease in pH levels, a process known as ocean acidification. This shift toward more acidic conditions threatens marine life, particularly organisms that rely on calcium carbonate to build their shells and skeletons, such as corals, mollusks, and certain plankton species. These organisms are crucial to marine ecosystems and food webs. Coral reefs, which support a wide variety of marine species, are especially vulnerable in acidification. Additionally, plankton species that form the base of the marine food chain are affected, potentially disrupting the entire oceanic ecosystem. Climate change is also impacting ocean currents, which are driven by temperature variations, salinity, and wind patterns. As the oceans warm and glaciers and polar ice caps melt, more fresh water is released into high-latitude regions, reducing the density of surface waters and slowing the sinking that drives deep ocean currents. This disruption in currents, such as the Atlantic meridional overturning circulation, could have significant impacts on global climate patterns, leading to shifts in weather systems and regional climates. These changes may affect heat distribution across the globe and alter nutrient flows that are vital for marine life. Moreover, ocean salinity is changing due to increased freshwater from melting ice and intensified precipitation, impacting thermohaline circulation, which is vital for nutrient transport and ocean productivity. High salinity regions are becoming salter, while low salinity regions are becoming fresher, indicating an intensifying global water cycle. These shifts stress marine ecosystems that depend on stable salinity levels. Additionally, ocean warming is reducing oxygen levels, especially in the Pacific, leading to expanded oxygen minimum zones and dead zones in coastal regions. The causes are the reduced solubility of gases in warmer water, increased water stratification, the higher metabolism of marine organisms, and algal eutrophication. Increasing wildfires. Climate change is significantly increasing the frequency and intensity of wildfires around the world. Higher temperatures lead to drier vegetation, which serves as fuel for fires. Additionally, shifting precipitation patterns can result in more frequent droughts and prolonged dry spells, further drying out vegetation and making it more flammable. Extreme heat also exacerbates these conditions, causing more intense and fast-spreading fires. The increase in wildfire activity is not only devastating to ecosystems, destroying habitats and threatening wildlife, but it also poses serious risks to human health and safety. Wildfires release large amounts of carbon dioxide and other pollutants into the atmosphere, contributing to air quality issues and climate change. Changes in biomes. Climate change is significantly altering biomes across the globe, reshaping ecosystems and impacting species distribution. As temperatures rise, many biomes are shifting towards higher latitudes and elevations. For example, tundra regions are transitioning to shrubland or forest, while temperate forests are moving poleward. This biome migration affects biodiversity, as species that cannot adapt quickly enough may face extinction. In the Arctic, the melting of sea ice is transforming polar habitats, while in tropical regions, increased temperatures and altered precipitation patterns are leading to shifts in rainforest composition. Additionally, climate change facilitates the spread of invasive species. Warmer temperatures and altered precipitation patterns can create more favorable conditions for non-native species to establish themselves in new areas. These invasive species often outcompete native species for resources, disrupt local ecosystems, and reduce biodiversity. Extinction risk. Climate change significantly increases the risk of extinction for many species by disrupting their habitats and altering ecological balances. Rising temperatures and shifting precipitation patterns can destroy or transform the environment species depend on. Vulnerable species, such as polar bears and certain amphibians, face heightened risks due to their specialized habitat needs and sensitivity to temperature changes. Additionally, ocean acidification threatens marine species that rely on calcium carbonate, such as corals and shellfish, impairing their ability to survive and reproduce. Effects on human health and migration. Climate change poses significant threats to human health and well-being. Increasing temperatures contribute to more frequent and severe heat waves, which can lead to heat-related illnesses and exacerbate existing health conditions, particularly in vulnerable populations. Changes in climate also affect the spread of infectious diseases. For example, warmer temperatures and altered precipitation patterns can expand the range of vectors like mosquitoes, increasing the incidence of diseases such as malaria and dengue fever. Additionally, extreme weather events, such as hurricanes and floods, can cause injury, displacement, and mental health issues. Climate change is also a major driver of migration. Rising sea levels, extreme weather events, and deteriorating environmental conditions force people to relocate, creating climate refugees. Migration due to climate impacts can lead to overcrowded conditions in receiving areas, strain on resources, and social conflicts. Effects on agriculture. Climate change has a profound impact on agriculture, affecting global food security and nutrition. Rising temperatures, shifting precipitation patterns, and increased frequency of extreme weather events can reduce crop yields and threaten food production. For instance, heat stress can impair plant growth and reduce the quality of crops, while altered rainfall can lead to droughts or floods that damage agricultural lands. Additionally, changing climate conditions can affect the distribution of pests and diseases, further compromising crop health. Economic analysis of climate change. The economic analysis of climate change involves assessing the costs and benefits of mitigating and adapting to its effects. Climate change poses significant economic risks, including damage to infrastructure, increased healthcare costs, and reduced agricultural productivity. On the other hand, investing in mitigation strategies, such as reducing greenhouse gas emissions and transitioning to renewable energy, can yield substantial long-term economic benefits by avoiding the worst impacts of climate change and creating new economic opportunities. Tipping points in the climate system. An issue of crucial importance in climate science is the concept of tipping points, critical thresholds where minor changes can lead to significant, often irreversible impacts through positive feedback mechanisms. Among these, the most dangerous is the potential collapse of major ice sheets, such as those in Greenland and West Antarctica. If these ice sheets reach a tipping point, they could rapidly disintegrate, leading to several meters of sea level rise over the coming centuries. This would inundate coastal cities, displace millions of people, and cause widespread economic and environmental damage. Another critical tipping point is the release of methane from thawing permafrost. Permafrost holds vast amounts of methane, a potent greenhouse gas. As global temperatures rise, the thawing of permafrost could unleash large quantities of methane, further accelerating global warming in a dangerous feedback loop. This process could lead to even more severe climate impacts, compounding the challenges of mitigating climate change and adapting to its effects. The uncertainty and potential for rapid, large-scale impacts from these tipping points make them some of the most pressing concerns in climate science. Of all the activities we engage in that have the potential to impact our climate, the most significant by far is our consumption of energy. Today, humanity's demand for energy is vast and ever-increasing, with the world currently consuming energy at a staggering rate of approximately 20 trillion watts, or 180,000 terawatt-hours per year. This is equivalent to keeping 200 billion 100-watt light bulbs glowing continuously. Per capita energy consumption is equally staggering. With a global population of over 8 billion, this translates to about 2,500 watts per person. To give you a sense of scale, the average human body at rest generates energy at a rate of about 100 watts. On average, each person on Earth uses energy equivalent to 25 times their own body's output. However, this energy use is not uniform across the globe. In the most energy-intensive countries, such as the United States and Canada, it exceeds 8,500 watts per person. So, what do we do with all this energy? Energy consumption can be divided into four main sectors. Transportation. About 35% of energy is used to move people and goods around. Industry. Around 31% of energy goes into manufacturing and industrial processes. Residential. Approximately 20% is consumed in homes for heating, cooling, cooking, and powering appliances. Services. The remaining 14% is used in services like in commercial buildings, healthcare facilities, educational institutions, entertainment and leisure. Our energy comes from a diverse mix of sources. In 2023 the composition is: fossil fuels, coal, oil, and natural gas still dominate the global energy landscape, making up approximately 82.5% of total consumption. Nuclear power, this contributes about 3.5% of the world's energy. Renewable energy, nearly 14% of energy comes from renewable sources like hydroelectric, wind, solar, and geothermal power. This energy mix varies by country, depending on factors such as natural resources, economic development, and policy choices. At the start of the century, in 2000, the percentages were 87%, 6%, and 7%, respectively. Excluding hydropower, the share of renewable energy, primarily solar and wind, increased dramatically from 0.7% to 7.7% in almost 25 years. When looking specifically at electricity production, fossil fuels account for 60.5%. Wind and solar energy have seen a significant rise, jumping from 0.2% in 2000 to 13.4% in 2023, now forming a substantial part of the energy mix with an obvious uptrend. This is crucial since the share of electricity in global final consumption is constantly rising. Carbon dioxide emissions from energy and industrial production have evolved over time, initially dominated by coal during early industrialization, with oil and gas gaining prominence by the late 1800s. Today, solid, liquid and gas fuels lead global emissions, while cement and flaring play smaller roles. Although coal emissions once dominated in Europe and the US, industrializing nations like China, India, and South Africa have seen a sharp rise in recent decades. Greenhouse gas emissions from the energy sector make up nearly 75% of global emissions, mainly due to electricity in heat production and transportation fueled by fossil energy. The agriculture sector contributes 18%, with key sources being livestock, rice production, soil management, and land use changes like deforestation. Together, these two sectors dominate global emissions, with energy largely driving carbon dioxide emissions and agriculture contributing methane and nitrous oxide, reflecting the different types of human activities fueling climate change. But, why should we care about energy consumption? It's not just about powering our lives, energy use is often closely linked to economic prosperity. Many countries with higher energy consumption typically have a higher gross domestic product, GDP, per capita. However, this relationship is not always straightforward. Some nations, particularly in Europe, use energy far more efficiently, achieving high GDP with much lower energy consumption. We can learn a lot from these countries about balancing economic growth with sustainability. But this raises a deeper question: is GDP the best measure of well-being? GDP includes all economic activity, even those that don't necessarily improve quality of life. Some economists argue that the United Nations Human Development Index, HDI, offers a more comprehensive view of well-being, incorporating factors like life expectancy, education, and literacy. Interestingly, the HDI shows that while energy consumption does improve human development up to a point, beyond that, more energy doesn't lead to greater well-being. This suggests that true prosperity might be better measured by how well we use energy, rather than how much we consume. So, keep in mind that the pursuit of ever-increasing energy production is not always synonymous with genuine progress or well-being. As we look towards a future where the impacts of climate change are increasingly apparent, it's clear that we must rethink our energy sources. If we can't eliminate carbon emissions from fossil fuels, we'll need to find alternative ways to power our world. Fortunately, Earth's natural systems offer several distinct energy resources, each with its own potential and challenges. Let's begin by exploring the concept of energy flows, streams of energy that continuously arrive at Earth's surface. The most dominant flow, by far, is solar energy, which accounts for about 99.98% of the energy reaching Earth. This solar energy drives various subsidiary flows, including wind, flowing water, and, through photosynthesis, powers nearly all life on our planet. To put this into perspective, the Earth receives more energy from the Sun in just 1 hour than the entire world uses in a year. If we could harness even a fraction of this energy, we could meet global energy demands many times over. A much smaller portion of Earth's natural energy flow comes from geothermal energy, which originates from the planet's hot interior and contributes nearly all of the remaining 0.02%. An even tinier fraction is derived from tidal energy, which results from the gravitational interactions between the Earth, the Moon, and the Sun. Next, we have fuels, substances that store energy. The fossil fuels, coal, oil, and natural gas are essentially stored sunlight, their carbon-based chemical structures capturing solar energy that was absorbed by ancient plants and organisms hundreds of millions of years ago. In contrast, nuclear fuels release energy through nuclear reactions. Currently, we harness energy from uranium using nuclear fission, but there's potential for much more. For instance, deuterium, a heavy isotope of hydrogen found in seawater, could one day provide nearly unlimited energy through nuclear fusion, a technology still under development. Today, we have technologies that can tap most of Earth's energy flows and fuels, but not all are equally mature or economically viable. For over a century, fossil fuel combustion has been our primary energy source, despite significant drawbacks like limited supply, greenhouse gas emissions, and pollution. Among fossil fuels, natural gas emits the least CO₂ per unit of energy, followed by oil, with coal being the highest emitter. Fossil fuels also severely impact human health, causing accidents during extraction and transportation, such as oil spills and mining disasters, and contributing to respiratory and cardiovascular diseases. Air pollution from fossil fuels leads to an estimated 4.5 million premature deaths annually, underscoring the human cost of these energy sources. Additionally, fossil fuels are not distributed evenly across the globe, which makes many nations dependent on imports, potentially hindering their prosperity and economic stability. Not related to the climate, it is worth noting that oil and gas reserves are expected to last only for a few more decades. As these resources dwindle, they may no longer meet growing global demand, which could trigger significant energy shortages and economic instability. If supply fails to keep up with demand, it could lead to sharp price increases, economic disruptions, and heightened geopolitical tensions, highlighting the urgent need to transition to more sustainable energy sources. Nuclear fission energy is a powerful source of low-carbon electricity, capable of providing large amounts of energy with minimal greenhouse gas emissions. It is reliable, with nuclear power plants able to operate continuously for long periods, making it a key player in efforts to combat climate change. However, nuclear energy comes with significant challenges. The risk of catastrophic accidents, such as those seen at Chernobyl and Fukushima, raises serious safety concerns. Additionally, the disposal of radioactive waste remains a critical issue, as it can remain hazardous for thousands of years. While advancements in waste disposal technologies, such as deep geological repositories and waste transmutation, are improving the safety and management of nuclear waste, these solutions are still in development and require careful implementation to ensure long-term security. Nuclear fusion energy holds immense promise as a future energy source, offering the potential for virtually limitless, clean, and safe power. Unlike nuclear fission, which splits atoms, fusion combines them, replicating the processes that power the sun. The key advantages of fusion include abundant fuel sources like hydrogen isotopes, minimal radioactive waste, and no risk of catastrophic meltdowns. However, despite decades of research, achieving practical fusion energy remains a significant challenge. The technology is still in its experimental stages, with major hurdles in sustaining the high temperatures and pressures needed for fusion. Nevertheless, with ongoing advancements and substantial international investment, fusion energy could play a transformative role in the global energy landscape in the coming decades. Geothermal energy, while a reliable and consistent renewable source, has some significant drawbacks. Its availability is geographically limited, as it can only be effectively harnessed in regions with high volcanic or tectonic activity. Additionally, geothermal plants can cause environmental concerns such as the release of harmful gases, including hydrogen sulfide, and potential groundwater contamination. The development of geothermal energy can also lead to land subsidence and require substantial upfront investment, making it less accessible and more expensive compared to other renewable energy options. Other renewable energy sources, particularly solar and wind, have experienced remarkable growth in recent years, showcasing their potential to reshape the global energy landscape. Simple passive solar technologies can be used for heating, cooling, and lighting buildings, while more advanced systems, such as photovoltaic cells, directly convert sunlight into electricity. Solar energy, in particular, has seen an astonishing decrease in costs, becoming one of the cheapest sources of electricity in many regions of the world. This rapid cost reduction is driven by technological advancements, economies of scale, and improved manufacturing processes. For example, the cost of solar photovoltaics has dropped by nearly 90% over the past decade. This makes solar power not only a viable option for reducing carbon emissions but also an economically competitive choice for energy generation. Wind power, an indirect form of solar energy, is another rapidly growing renewable resource, especially for electricity generation. In regions with strong wind resources, it can meet a substantial portion of energy needs. However, due to its intermittent nature, wind power is typically relied upon for only a fraction of the electricity supply. The average cost of onshore wind energy has fallen by about 70% over the past decade, with prices now averaging around $33 to $55 per megawatt-hour globally in 2024. Offshore wind, while initially more expensive, is following a similar trend with costs decreasing as technology improves and deployment scales up. In areas with strong wind resources, onshore wind can now compete directly with fossil fuels, providing a substantial portion of energy needs at a lower cost. Hydropower, which harnesses the energy of moving water, is a well-established technology. However, its growth potential is somewhat limited, as most suitable sites for large dams have already been developed. On the other hand, tidal and wave energy, derived from the movement of ocean waters, are emerging technologies with significant promise, particularly in coastal areas. While still in the early stages of development, these sources could provide consistent and reliable energy, complementing other renewable sources. Biomass energy, sourced from organic materials, offers a unique advantage. It is one of the few renewable sources that can be directly used for transportation fuels. Importantly, biomass is considered a nearly carbon-neutral energy source because the carbon dioxide it releases when burned is roughly equal to the amount absorbed by the plants through photosynthesis during their growth. However, the environmental benefits of biomass depend on how sustainably it is harvested and processed. In regions like Brazil, which efficiently convert sugarcane into ethanol, demonstrate how biomass can significantly reduce carbon footprints when done right. Hydrogen also holds promise as a clean fuel, as its combustion produces only water. However, hydrogen does not exist freely in nature and must be produced from other energy sources. Therefore, its environmental benefits are closely tied to the methods used for its production. For hydrogen to play a significant role in the future energy landscape, it will need to be generated using renewable or nuclear energy sources. Despite the rapid growth of renewables, we must recognize that no energy source is without its challenges. Solar panels require energy-intensive manufacturing, hydropower dams can have significant environmental impacts, and nuclear power raises concerns about long-term waste management. Moreover, while renewable energy sources generally produce far fewer greenhouse gas emissions than fossil fuels, they are not entirely emissions-free. However, the future of energy is not just about which sources we use, it's also about how we use them. Electrification, particularly in sectors traditionally dominated by fossil fuels, such as transportation and heating, is a crucial step towards a sustainable energy future. Electrification allows us to tap into renewable electricity, thereby reducing dependence on fossil fuels and significantly cutting greenhouse gas emissions. According to the International Energy Agency, electrification, paired with a shift to renewable energy, is one of the most effective pathways to achieving net zero emissions by mid-century. To address climate change, the goal is to stabilize greenhouse gas concentrations at levels that prevent dangerous interference with the climate system. Scientists have identified a doubling of pre-industrial CO₂ levels, from 280 ppm to around 560 ppm, as a critical threshold for danger. Currently, CO₂ levels are about 420 ppm and rising by 2.5 ppm each year, putting us on a path to exceed this threshold. The Paris Agreement aims to maintain current levels through the end of the century, but projections suggest we could surpass 500 ppm. If this occurs, global temperatures could increase by 3 degrees Celsius above pre-industrial levels. To understand the gravity of this rise, one can compare it with the global temperature fluctuations over the past 2 millennia, highlighting the unprecedented nature of such a change. To minimize this risk, several strategies are being considered. Global engineering ventures. We might consider large-scale geoengineering projects to counteract greenhouse gas effects. Some proposed methods include orbital mirrors, placing mirrors in space to reflect sunlight. Injecting sulfur particles, this would reflect sunlight away from Earth, in a way copying the volcanic effect. Ocean fertilization, adding iron to oceans to boost phytoplankton growth, which absorbs CO₂. However, these methods are highly speculative and could have unintended consequences due to our limited understanding of Earth systems. Carbon capture and sequestration. Another approach to reducing CO₂ emissions is to capture and store them before or after they reach the atmosphere. Carbon capture. Technologies capture CO₂ from power plants, but dealing with massive volumes, tens of thousands of tons every day from a typical plant, and nitrogen separation remains challenging. Direct air capture, DAC. DAC removes CO₂ directly from the air, offering flexibility but requiring significant energy, though renewable sources may improve efficiency. DAC is crucial for achieving negative emissions. While it is still in the early stages of implementation, with several small-scale plants in operation, the goal is to dramatically expand DAC capacity by 2050, potentially scaling up to remove hundreds of millions of tons of CO₂ annually to meet global climate targets. After capture, the next stage is sequestration. In this process, CO₂ is stored in secure geological formations such as brine-filled aquifers, old oil fields, or the deep ocean. This combined approach, known as carbon capture and sequestration. Transition to alternative energy sources. Switching to alternative energy sources can also help. Nuclear energy provides about 10% of the world's electricity. It has potential but faces challenges like radioactive waste and safety concerns. Hydroelectricity, one of the largest-scale renewable sources but with limited new potential and environmental impacts. Renewable technologies, solar and wind energy hold significant promise. Solar photovoltaic, in particular, has seen dramatic costs drop in the past decade, making it highly competitive. Wind energy is also growing rapidly, with advancements in turbine technology and offshore installations enhancing its viability. As these technologies advance, they are expected to become even more dominant in the global energy mix, surpassing traditional sources in both capacity and cost-effectiveness. Solar PV as well may surpass wind energy in terms of both capacity and cost-effectiveness. Energy efficiency. Improving energy efficiency is a key strategy in reducing energy consumption and emissions without sacrificing comfort or quality of life. For instance, enhancing insulation in buildings can reduce the need for heating and cooling, while energy-efficient appliances like LED lighting and high-efficiency refrigerators consume less power. In industrial settings, optimizing processes to use less energy can lead to significant reductions in overall consumption. These measures not only help to lower greenhouse gas emissions but also reduce energy costs, making them both environmentally and economically beneficial. Forest conservation and reforestation. Stopping deforestation and actively planting trees are crucial strategies in combating climate change. Forests play a vital role in absorbing CO₂ from the atmosphere, acting as natural carbon sinks. Protecting existing forests and expanding forested areas are key steps in reducing overall greenhouse gas levels. Reforestation efforts can help offset emissions, restore ecosystems, and contribute to a more sustainable balance of carbon in the atmosphere. After examining all these solutions, it's clear that no single approach will be enough to combat climate change effectively. A comprehensive strategy that combines multiple methods will be essential. Only through a multifaceted approach can we hope to address the complexity of climate change. To sum up, the current rise in global temperatures is strikingly atypical, even when viewed against the backdrop of thousands of years. This unprecedented warming is not only evident from historical temperature records but also reinforced by other alarming indicators, such as the rapid melting of polar ice and rising sea levels. These changes signal that today's climate shift is driven by extraordinarily high levels of greenhouse gases, a phenomenon that stands out from natural historical patterns. The primary source of these emissions is the combustion of fossil fuels, which has surged in our relentless pursuit of energy. As a result, greenhouse gas levels have reached unprecedented heights, further accelerating the warming trend. The trajectory we're on suggests even more severe implications for the future. To address this critical issue, humanity must urgently act to eliminate emissions and even explore methods to remove carbon from the atmosphere. This will require a comprehensive strategy, including a significant shift towards renewable energy sources and enhanced energy efficiency. The urgency of this transition cannot be overstated if we are to mitigate the adverse effects of climate change and secure a sustainable future for generations to come. We must act now.